Newton's law of cooling is one application of differential equations, and it's quite a nice one. So it states here that the rate of cooling of a body is proportional to the temperature difference between the temperature of the body and the temperature of its surroundings. So when we're talking about a body, that's anything. It doesn't have to be, a thing that was once alive, or it can be a block of wood or a piece of metal or a cup of coffee. So we're talking about a thing that has some mass and is found in some surroundings. So if we are thinking of a body, then usually the temperature of its surroundings would be air temperature. If the thing was floating in the water, it would be water temperature. It's that kind of thing. So whatever the stable temperature of the surroundings are, is what that is. So let's write that up as a differential equation then. So we're going to put d capital T, d lowercase t, in other words, the change in temperature over time, is equal to negative k. Okay, negative because it's cooling and therefore the temperature is going down. And then we use the temperature minus T0, where T0 is the temperature of the surroundings. And usually that's air temperature. So let's just make a couple of notes of this. So we've got the body temperature, that's that T there, that T there, that little t is time. This is usually air temperature, but it's just the temperature of the surroundings. And then K, of course, is that proportion. Often that's the proportion we need to work out. And negative because it's going down. It's that idea of cooling. Right, well, let's work with this equation to turn that into something useful. So we've got dt by dt, negative k, t minus T0. Now, of course, the active variables are the body temperature T and the time. So T0, the temperature of the surroundings, is actually treated as a constant. So we're going to create an equation out of this by separating variables. So if we go ahead and do that, then I get 1 over T minus T0 dt is equal to negative k dt. And we can take the integral of both sides. If we do that, I get log T minus T0, and I'll put a capital A in front of that. Usually we use a K, but I've already got a K, so we'll use A instead, and that becomes negative K T. So we've done that. And then lastly, what we do is sort of anti-log it, and therefore I get T minus T0 is equal to A, E, because that A can just switch sides to the negative KT. And then if we make T the subject, I get T0 is equal A, E to the negative KT. And that's the equation of Newton's law of cooling, and we just managed to squeeze that in. So let's go ahead and solve a problem. So here's Bob the sperm whale, and it's got a whale is found dead underwater in the sea. When it is found, its temperature was 33 degrees, and 2 hours later, it was 29 degrees. The sea temperature was measured at 18 degrees. All right, well, we've got some information that we can work with. Let's write that down. So first of all, the very first temperature that we take, we're going to make that time is equal to 0. And that's important because that makes our calculations a lot easier. Okay, so we make that T0. And then 2 hours later, we're told the 29, that's 29 degrees, and T0 is equal to 18, which is the water temperature. So we've got enough to work with there. And what we need to do is we need to create an equation for that. So let's write out what we've got. That's equal to T0 plus AE to the negative KT. All right. T0 is equal to 18. Actually, what we're doing is we're going to substitute in that to start with. So we need to solve the equation here. I was rushing ahead, all enthusiastic, but we need to solve it for A and for K. So we'll go ahead and do that. So T0 is 18, T is equal to 33, and T is equal to 0. So A, E, K times 0 is 0. E to the 0, everyone knows, is 1. So from that, I think we can work out that A must be equal to 15. 15 plus 18 is 33. So A is equal to 15. Right, well, we carry on now. So I've got, not 33, get rid of that. So we can substitute that in there. Come on, behave. T is equal to 18 plus 15, negative KT. So the next job is to work out, well, what is this K equal to? And we use the next set of data to work that out. So we're going to substitute that into the equation to work that out. So the temperature is 29, the temperature of the whale is 29. Still got that 18, still got that 15. And after 2 hours, so our time now is in hours, we just need to be aware of that. So that becomes negative, let's put that negative 2K. And we go ahead and solve that. So we subtract 18 from both sides and then divide by 15. So I get 11 over 15 is equal to, there's an E missing here, isn't there? There we go. We'll squeeze them in. And that's equal to E to the negative 2K. Log of both sides. So we get the log of 11 over 15. Now the log of E, when we're using natural log, that just disappears. So that becomes negative 2K. And then using the calculator, we can work out that K when we do that. Take log of K divided by negative 2. And we get K is equal to negative, no we don't, we get 0.1551. So we now have an equation to calculate the cooling of the whale. So T equals 18 plus 15 times E to the negative 0.1551 T. So we can now use this to go ahead and work out some other stuff. I've got a little graph. There's the graph of it, actually. If you look at it, I'll just move that up. Graph. Okay, so that is the graph of the equation that we've got. So you can see the thing cooling down. And here's your initial temperature of 33. There it is there. And here's your 18, and you can see this line gradually tracking down to the temperature of the sea. And eventually the body will cool down to 18 degrees. It'll do that. And of course, if the body's been in there too long, then we can't work with it anymore. But we're good here. So there's the graph. So let's carry on. What was the question? We've got some questions over here. Okay. When will Bob's temperature, or what will Bob's temperature be after 10 hours? Look at that test. Lost it for a second. After 10 hours. Okay. Well, we've got the equation. So all we do is we substitute 10 into this. So we'll make that question A. T is equal to 18 plus 15 times E. Now 10 times this is negative 1.551. And you just do that on your calculator. All right, T is 10. And 10 times that is what we've got. Okay, that's where that. So it's just straight substitution. And if you work that out on your calculator, then you find T is equal to 21.18 degrees, which we'll round off to 21 degrees. And you need to remember too that there's a whole lot of factors involved here that will affect the accuracy of the result. For example, is the sea temperature constant the whole way through? Is the whale submerged the whole time, or is it at the surface some of the time? Things like that. So, but that's good. We've got that 21 degrees there nicely. So let's look at the next one there. How long will it take Bob to cool down to 25 degrees? Well, we use our equation again. We use the same equation, but this time we set it equal to 25. And what we're doing is instead of working out a temperature, we're now working out a time. So it becomes an index equation where we need to work out what T is equal to. So you can probably guess there's going to be some logs involved there. So if I subtract 18, divide by 15, we end up with 7 over something, 15. Yes, we do. And that's equal to e to the negative 0.1551 t. Log of both sides, log of 17 over 15, and that's equal to 0.1551 t. We work that out. We will get an answer of 4.9 something. So in other words, it's going to take about 5 hours. So, all right, so we can put that down. And we get 5 hours for the body to cool down to this temperature. Now the last one, this one is actually used in forensics to calculate time of death. So if there's been a murder, then this is the kind of thing that can be done to calculate the time of death. And it says if Bob was discovered on Thursday at 10 a.m., when did he die? Now, to know that, we need to know that the normal body temperature of a sperm whale is 38 degrees. And so what we're doing is we're working out what time was it then when the body was 38 degrees. So we said 38 degrees is equal to, where's our equation again? 18 plus 15 e to the negative 0. I've written this out so many times, I remember that now. There it is then. And again, we're working out T. So it's interesting here because that's higher than the start temperature of 33. So we're probably going to anticipate that we will get a time that is negative. And that'll be true because we're going back from when we found them. And so it might be 1 hour, 2 hour, 3 hour, 4 days before we found them. And so it'll be a negative answer indicating that it was before that T is equal to 0 that we set to begin with. No problem. So we go ahead and do that, and we get 20 over 15 is equal to e to the negative 0.1551 t. Log of both sides, 20 over 15 is equal to negative 0.1551 t. And on the calculator, when we work out what t is equal to, we get negative, as I indicated, 1.854. And that's pretty close to 2 hours earlier. In other words, if he was found at 10 a.m., so when did he die? Well, he died at about 8 a.m. the same day. You can, if you want to work out exactly what that is in minutes, and I think if you do that, you get 1 hour and 51 minutes, if you want to be fussy, and that makes it 8:09 a.m. But remember, there are certain inaccuracies in the process. That'll do us.